the process of doing it, you will on with an interesting exercise to begin the day. And then we'll get into the branch and bound, how we use branch and bound to solve the knapsack problem. Things to do it, but how does branch and bound help us to solve the knapsack problem, you will learn here. And a couple of other problems too. Okay, last in, first out, first in, first out. We'll see a couple of nice, interesting examples today. Class will be a breeze. Hopefully you'll not get lost. Even if you get lost, don't despair, because when you do the exercises that follow the topic, you will appreciate it and gain a good understanding. Having said that, take about 7 minutes to 10 minutes, or maybe 7 to 10 minutes, you should be able to solve this problem. I will introduce the problem to you, then I will go on mute, okay? Groups of 2, okay? Instructors, please facilitate groups of 2, right? So we have a US Navy. You can call it Indian Navy too, right? Indian Navy is quite good now. Okay? Actually, think of Indian Navy as think about that wonderful movie that you have, right? What is that? Ghazi Attack or something like that? That movie that came, which was a big hit. So you have this team called SEALs. SEALs are like the highly specialized US Navy force, okay? They are the best. We call it like, what do you call it in our English lingo, right? Hyderabadi lingo, we call it the bestest, right? They are each specially trained in a wide variety of skills. So that means they have some skills, okay? And each of them comes up with a multitude of skills. Okay? They can handle many, many missions together. So in an abstract way, there are K different skills needed for a mission. Okay? So whatever mission that is, maybe killing, finding Al-Qaeda leader and when they killed, right? That was a mission. Okay? So you have K different skills that are required, and then you have N SEAL members, K and N, okay? And they can be assigned to the team, right? The goal is to find the smallest team that will cover all of the required skills. Everyone understand the question? So you have a mission to do. In order to do that mission, there are K different skills that are required, okay? So what is the smallest number of members that you can have? Between them, you cover all those skills. Okay? So I have given a list of names here. You can, of course, change the names to your favorite movie stars. I would not mind. Make Anderson something like Butler. Maybe Brahmanandan, that sounds like Brahmanandan to me. Cunningham, hand-to-hand combat, Douglas. Okay, so the skills are comma separated. As you can see, they're different skills, different people. Okay, find the smallest team that will cover all of the required skills. Okay, ready, set, go. Write it on a piece of paper because I want to see how you solve it. It's easy to solve visually, okay? But it's important to understand your thinking process, how you solve it, okay? Now that you have done enough of algorithms in this class, you should be able to document your algorithm, how you solved it. Because after you solve it, I would ask that question. Explain to us how you solved it, okay? I will go on mute. I'll get my cup of tea so that way I would not fall asleep. College of Engineering. Everyone agrees? Do students have any other solutions? That looks like it, right? Okay. Who else got the same answer? Did PVP Siddhartha, did any of the students sitting there, did you get the answer the same too? You can raise your hand if you got the same answer. Nobody got the same answer? Nobody raised the hand? If you got the same answer, I said raise your hand. right? Okay, now the question is, how did you arrive at the answer, right? So I don't see any videos other than PVP right now. Classes, they are also not recording and there are no students there. Let me move the screen. So what was the algorithm behind it? Can anyone tell me? How did you arrive at that answer? That's what I'm trying to understand. How did you? And the second question is this a knapsack problem? Okay. The only video I see is PVP Siddhartha, as I mentioned, right? So let me ask them for a show of hands there, right? The professor is there sitting at the front. So since he's a faculty member, he has been there right from day one. I'm very thankful to him. Is this an abstract problem in essence? Raise your hand if you think it's an abstract problem. I'm only seeing left side of the screen, not, because the faculty member is blocking the right side there. And then you have certain weights, right? Here the backpack is nothing but your mission, right? It requires certain skills, right? So you have to substitute those words. Even though when we introduce knapsack, we talk in terms of weights and backpack. It's really about all other things, right? So it is an abstract problem. Okay. Now, if it is an abstract problem, how did you solve it? I asked. Now you can answer the first question. How did you arrive at the answer? Question is open for all the other colleges too, not just PVP, right? Can I say that I arrived at an answer? I'm looking at this. I know what are all the skills that are required, right? It's easy to count the skills, right? And then do I start with the person who has the maximum number of skills, and then go from there? That's a possible solution, right? Because then I go down the branches, I will see who else has the other remaining skills, and then I stop once I cover the full set. Does that sound like an algorithm to you? Right? You should be able to explain those things when I ask you those things, right? That's how the exam questions would be. I would still give an exercise like this as an exam question. I would say, okay, what is the answer? Explain how you arrived at the answer. Write an algorithm for that. Okay. Now, once I write an algorithm, would it be easy for me to also ask you then, what is the complexity of your algorithm? To be able to, right? Remember our theory, right? We're coming towards the end of the semester here, right? I count the loops. If there are any loops, I know how to arrive at the ON squared and all of those things, right? If there are no loops, if it's based linear, it's based on n only, then I say order of n, right? The concepts are very simple, absolutely simple, right? And if I'm doing a brute force way of figuring it out, remember we talked about 8 queens problem, right? Or 4 queens. What did we do there to place the queens? We looked at all the combinations. We said the brute force way would be 2 raised to n, whatever the n is, right? It's a fact. It's an exponential thing, right? So you should be able to arrive at those things, whether it's a linear, whether it is logged, or whether it is exponential or n cube, different things. Of course, when you get deep into research, you will come up with very finer nuances of those that framework. But for normal human beings and normal algorithms, those things should be good. Linear, square root, n squared, n cubed, factorial, right? Or exponential. Okay. So that's so as we agreed, it is an abstract problem. Give me a second. I'm trying to adjust my window so that way you can view it. Okay. So what is an abstract problem again? The input is capacity K. Okay. And we have n items with weights. Remember, whenever we talk about items, we talk about weights and values. Okay. And the output is a set of items S such that the sum of weights is at most K, because it has to be less than or equal to K, the total capacity. And the sum of values of items in S is maximized. Okay. That is what the knapsack problem is. Now, we have given examples in the past where the greedy does not work, right? Okay. Why? Because it's not necessarily like you can either take the I'll go from the highest density first. Okay. It could be highest value. Highest density is really, I think it is the highest weight. Okay. You can do the highest value first, or you can do the lowest weight first. Okay. We have done some examples. You refer to them. It's a good exam question, right? Give me an example scenario where the knapsack greedy does not give an optimal solution. If you go back and look at the practice problems that we did in the class, there are a couple of practice problems where it shows you that. Okay. Now, dynamic programming does not work when the problem cannot be described as integers. Okay, if it's fractional, then dynamic programming doesn't work. Okay, like for example, here you see the items are A, B, C, D, E. Okay, item weight is 2 units of something, right? Pi is not integral. Same thing, WC 1.98. Dynamic programming doesn't work there. So when it doesn't work, then we have to do the brute force, right? So when you do the brute force, okay, brute force means generating all possible solutions. Okay? So for the n items, the possible solutions are 2 raised to n, right? So if you have 3 items, 2 raised to 3. Remember, you learned binary logic, right? So if n is 3, 2 raised to 3, 8 combinations. Because remember, when you have 3 items, you know how to do the binary number system, right? 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 1. Those are 8 combinations. So that is brute force. Now, you get the brute force approach to make sure, and then you then say out of those combinations, which of them satisfy the constraint. Constraint is the knapsack weight. Knapsack, how much it can hold. Now, out of the remaining subset, you find the maximum solution that satisfies the constraint. Now, remember I said all of these things can be converted into tree-based algorithms, right? So we can generate that as a tree. Very important to know how this tree is obtained, okay? Pay very close attention to this. Looks simple, but takes a little bit of time to assimilate, okay? I see this wonderful girl talking to somebody to her side who I cannot see. At PVP Siddhartha. Okay, focus on the screen unless the screen is on the right. Okay, so what are we doing here in brute force search? We started off with A. Okay, A is the, remember we have the items as A, B, C, D, E, right? Keep that in mind. Okay, we are starting off with, By the way, when I do this slide sometimes, right, even I may screw up. Correct me, okay, when I screw up. Because I prepared these things over periods of time, right? If I'm just looking at it all of a sudden, even I get confused sometimes. Yeah? Meaning you have a knapsack, we say, let's assume A is in. Okay? Or A is out. There are only two branches. You're representing as a tree, right? You can either put A in the backpack or you don't have to put A in the backpack. So A is in, then you come to B. Okay? So now you put B. B is either, sorry, I should. See, I told you I can screw up sometimes. I screwed up the explanation. Start over, okay? Control Alt Delete. Let's start over. We are starting with A. Okay? We are starting with A means A is already in the backpack. We took the very first item, put it there. Now we have a choice. Choice is the next item B. B can be in or B can be out. Okay? So B in is one branch, B out is another branch. You get it? Now, when the B is in or B is out, then you get to C. Right? Next level. C is in or C is out. Okay? Then you go to the C level. Then you say D is in or D is out. Then we go to D level, E is in or E is out. Okay? So now you can put the weights and the values, right? Whatever is in, if you follow the in branch all the way, right? If you follow the left side of the branch, depth first search, right? A, B, C, D, E. Okay? The value is, if they're all in, the weight is 15.12 and the value is 315. How did you get that? Because everything is in there, right? Left side. So A, B, C, D, E. So if they are all in, we're 3.14. Okay, that's 5.14, 6, 11, 14, 0.14 and 0.98 you add, it comes to whatever that 15 point something. Okay, and if you add all the values there, 40 plus 50, that's 90, 90 plus 100, 190, plus 95 is 280. Those values, it's 315. If you add the weights, it comes to 15 point something, right? So the left side value, if you see all the way, A, B, C, D, E, at E we stop, right? E is in. Okay, so the weight would be 15.12 and the value is 315. Okay, now if you follow the other part where we say C, if you see the weight 8.98 and the value is 235, same thing. Some of them are in, some of them are out. So that is how you compute at the leaves. Okay, if you compute these things at the leaves, then you see which of those leaves are valid, right? You cannot exceed a certain weight, right? You eliminate those branches or those leaves or the branches that lead to those leaves. And out of the remaining, you take the maximum value. Okay, this is brute force search, right? These are all the branches for that. How many branches are there? Do you know? If you count the leaves, how many are there? 32. And how did you come up with 32? 2 raised to 5. There are 5 items. So remember we said 2 raised to n. 2 raised to 5 is 32. Okay. So basically what we are doing in the case of backtracking, between backtracking and branch and bound, right? In branch and bound, we do breadth first, whereas in backtracking, we do a DFS. Okay. So in the case of backtracking, when we reach a point, meaning you have exceeded the weight of the backpack, then you don't need to continue along those branches any longer. Okay, so you backtrack instead. So in the process of backtracking, you say, okay, this branches of the tree we no longer need to consider. Okay. Okay. So that it basically shows which of them need not be considered. It was exceeding the weight. So then he shows what are the other two. 5 seems to be the right solution. Okay. So I put the values there. Okay. Now, what is the key differentiator for branch and bound? He said we know some kind of a solution which would work. Okay. We use that as a bound. That's what we did last class, right? We had one tour. Remember when we were visiting, when we did the traveling salesman problem, we had one candidate tour. So we know what the value is. As we are considering other tours, if the solution that we come up with is better than the bound, we continue. If it is worse than the bound, we ignore that path. That is the bound, right? Okay. So we need to come up with that bound, right? Somehow if we know what is that bound, then it becomes easy. Okay. So you know that when you go from A down, okay, the value is 315. And if you do only from B down, the value is 275. And from C down 225, that you can see, right? Because 275 plus the value of A was what, 40. That's how you came up with 315, right? So those are the values depending on which path you take. Okay. So as soon as we choose D, as it says here, okay, we are already overweight. So when you do A, B, C, D, nowhere here I gave the weight D. What is the weight limit of the backpack? Did I say it anywhere here? So when I calculate ABC weights, what are the weights of ABC? 2 pi is 3.14. So that's 5.14, 7 point something. Okay. The moment you add 5, it is becoming 12. I think the weight limit was less than 10. 10 is the weight limit. So I know that the moment I add D, I exceed the weight. So all the branches D and down below D, you ignore. You don't need to reconstruct them, like in brute force, because you already exceeded your objective function. In this case, weight has to be less than 10. Okay. So that is the pruning of the tree, right? That's what we are doing there. Okay. Okay. This example shows A to Z deep, meaning if they're F, G, H, I, and so on, right? You have cut an entire subtree from needing to be checked. Okay, you're with me so far? The trick is to come up with a candidate solution. And then as you build a tree, if it exceeds that weight limit, in this case it's a knapsack, then you eliminate that. You don't need to compute that. Okay. Any questions? Now, is it a hot summer day there in your place? I do see fans going full speed ahead on the ceiling. But I also see some students using their book as a fan. The girl wearing something like a reddish black, some dress. Okay. So the key to branch and bound is having a good initial. Okay. Here are the solutions. See, now you have to exercise your brain a little bit, right? How do we come up with that bound, right? He says, okay, can we start off with the highest weight first, right? Because we are trying to come up with the initial bound, right? So the author is saying, okay, what happens if I start building the tree with the highest weight first, right? How did we build this tree here? We just started, the first item is A, second item is pi is B. We just started off with the first item. No particular logic there, right? First one. However, here we are saying what happens if we build it from highest weight. When you do it with highest weight, in a way, that's what the solution was, right? In the beginning of the class, like the exercise, whoever came with that solution, they said, they took the person with the maximum amount of skills. Right? That's the weight. That way they can eliminate the infeasible solutions quickly. Okay? Highest density first, generate good solution quickly. Okay? Now, depending on the input, you choose the methodology, right? It all depends on input patterns. Okay? So let's see, here is an example, right? You started off with D at the top. D is the heaviest. If you go back and look at the first few slides, you'll see D's weight is the highest. Okay? Look at how small the tree is compared to the previous one where A was the started off with A for comparison. Keep this snapshot in mind. I'll switch some slides here. You can see how big this tree was. You see the difference? You build a tree starting with A, you get such a big tree. Whereas you start with D, much smaller tree. Smaller means more efficient, right? Again, unless you practice these things, you will not remember them, right? They get hardwired. I don't know if I told you this or not, right? I learned this from my brother-in-law once. Apparently, when you read a book 21 times, okay, any book, if you read 21 times, your neurons in the brain get connected, so well connected. We all have neurons in the brain, right? Other than politicians, maybe, okay? At least we do, engineers. So you would remember even to the paragraph, even the sentence level, you would know, okay, this paragraph came on this page. Apparently there's some theory, the cognitive science theory behind it, right? And that's why, obviously we don't have time to do 21 times of everything, but we do, I make you practice a lot. That's how you can internalize these concepts. Okay. So that is that. Now, best density on top. I didn't quite understand what density was. Was density based on ratio? Let me see. So C, why is best density? C is best density. Can somebody tell me? Let me see. Density, basically best value on top. He took the best, biggest bang for the buck. Okay. So it is really 1.98 over, it's the value, the maximum value that you're deriving, right? Lowest weight, maximum value. Correct? Isn't 1.98 the lowest weight? That's the density, right? Lowest weight, maximum value. It is a comparison, right? Weight over value. Okay. So by doing C on the top, you can see, you get a picture like that. Okay. So it really depends on which one you do. So it's like a best guess, right? So the more practice you get about these things, that's your subject matter domain expertise, you will have that gut feeling. If I do it this way, it might work better. Okay? That happens all the time in industry when we are solving problems, right? Subconsciously, we already come up with an algorithm based on our experience because we know it works. We were discussing like a very interesting example, actually, coming to think of it. We have what is known as a spring break week coming up in about a month. Spring break is nothing but, Easter, right? You all know Easter weekend, right? What do you call it? Good Friday in India, right? So here schools get 1 week holidays for that. And then the spring break week, we have to do college visits to our 2 daughters. My twin daughters, they are in 11th grade. So this summer, they'll be applying to colleges. Not like in India where you take an entrance exam, right? We apply to colleges here. Write something about what this college. One way they do is by visiting the colleges. And the spring break week is the most crucial break for the students in 11th grade because they have to visit the colleges. So you have a big list. Okay, the MIT, Harvard, these are all like the blue chip colleges, right? They are like the IITs and all that. And then we have to go to different cities. It's planning, right? So what did we do? My son, who is a Berkeley EECS graduate, is a computer science from Berkeley, right? Now he started applying this algorithm subconsciously, right? We don't have to think, it just happens, right? He came up with an optimization algorithm to say, what is the easiest route to take, right? And then how do we navigate all the cities? Shortest route. Remember Dijkstra's algorithm. We are essentially applying Dijkstra's algorithm to route our about 6 or 7 different colleges. Okay. Okay. Now, a couple of other notes here, right? What happens if half of the inputs to the knapsack problem all have the same weight? Okay. If all of them have the same weight, we could implement a greedy solution. Okay. But unfortunately, only half do not have it. Okay. Half of them may have the same weight, but other half do not. So what do you do there? You combine the approaches. Nothing is telling you that you can only use one way. It's called a multi. My professor used to call it, Professor Ramamurthy, who passed away exactly 1 year ago at the age of 90, my great mentor. He used to tell me, Pratap, in the world today, we cannot solve problems using one paradigm, one approach. You need what is known as a multi-paradigm approach. Like object-oriented programming is one approach, okay? Structured programming is another approach. There are different paradigms, okay? Event-based programming, constraint-based programming. These are all the things that you will learn as you study more and more computer science courses. So you need a multi-paradigm approach to solve problems. Same thing here, greedy and brute force. So what do they say? You apply for one half, you apply greedy. For the other half of the data, you apply brute force. Okay. See this picture shows you one half of the tree. You take care of it through greedy, and the other half you take care of it through brute force. Okay. So you're backtracking on half of the inputs. Okay. And then at the leaves, you're applying the greedy strategy. Okay, on the other half of the inputs. Okay. So what is the benefit that you're getting? If you apply brute force to everything, it is 2 raised to n. We already know that, right? Brute force 2 raised to n. N inputs, 2 raised to n is the brute force approach. If you apply combination, it turns out it is n 2 raised to n over 2. Now you would ask, what is the big deal of that combined approach, right? Look at the example here. Okay. If you suppose n equal to 50, there are only 50 items. 50 is not much. And then approaching your computing power is 1 million solutions per second. So you can see 2 raised to 50 takes 35 years. And 2 raised to 25, half of that can be done in half an hour. Real quantifiable data, right? So good question for, I don't know how your examiner set the exams. Okay, I have not seen how these exams are set in India. That's a great question, right? You say, justify why combining approaches would make sense. Give an example. I would choose half hour over 35 years any day. Okay. So you have other combinations. If knapsack has integral weights over values, meaning there are integer numbers, right? And then while the other half have real weighted values, if they're integral values, I can use dynamic programming techniques, right? The other one I can use brute force. Okay. Okay. So if you look at the n queens problem now, right? You all know what the n queens problem is, right? To place n queens on a board. I'll go fast here. Okay. If you were to do pure brute force search, you can see a 43,680 possible solutions. Okay. Now, by using your knowledge that only 1 queen per row can be there, right? You can quickly eliminate all the most of the 43,680 solutions, and there are only 256 possible solutions. Okay. So these are the kind of heuristics of data that you use to reduce how much time it would take. Okay. I gave some additional data here. Again, you have to just convince yourself. I don't have to explain all of these things to you in gory detail. Okay. You can see if n equal to 8, you can see 8 raised to 8 is 16 million solutions. Sorry, I don't know how to say it in crores. What is it? I don't know. Units, 167 lakhs. I can tell you that, 167 lakhs. So whatever it is in crores, okay? Okay. This was the problem, right? That I first gave you. By now, you pretty much know my trick. I give you a problem from the class, what I'm teaching, and then I'll make you think, and then we review the stuff. So what are we saying? We got this, right? Okay. I don't have time to do it in the class today, but then these are the things, food for thought for you after the class is over today, okay? So what kind of greedy algorithm you would use? What is the brute force approach? Draw a tree depicting the brute force approach. Okay, very interesting, right? You already solved the problem, correct? But then, if you go back, you should now know how to draw a tree for the knapsack problem in the class. Similar trees you should be able to draw for the Navy SEAL problem. Okay. I'm not giving you a break to do the problem now. I'll finish the module or come as close to finishing it as possible. Give me a second here. My mouth is dry. I need my tea here. Okay. So I have another exercise here where we are talking about how can we simplify the problem, right? Meaning how can we set bounds on the solutions? Okay. Same thing. See, remember the same knapsack is solved in different ways, right? So you should know, hey, what kind of a boundary I can set. This is a branch and bound, right? We are in the branch and bound chapter. So you should be able to take the same problem and say, okay, what could be a good bound for me here? Okay. So again, you have to think through that, solve it with a paper, pencil in hand as a group. Then you will start assimilating stuff. Okay. Okay. Moving along, any questions? So another interesting aspect of branch and bound is oftentimes when we are trying to solve problems, right? Cost is always a factor, right, for us. You want to have a least cost solution, right? When you are building a house, for example, cost solution. Of course, you have too much black money, then highest cost solution. But normal middle class, we always want to save money. So we are always looking at least cost solution. That's what traveling salesman problem 2 is, right? It is the least cost solution, right? Shortest distance. Distance is time and time is money. Okay. So what do we do here? This might take a little bit of homework for you to understand it. I'll explain the topic. Then once I upload, I think I already uploaded the slides. So review the slides carefully with the example. And then you come back to me with questions in the next class. Okay. So least cost solution is about cost approximation. Okay. Cost is what traversing of a tree. Remember, everything by now, you know, these solutions are done through trees. Okay. So every node X in the search tree is associated with the cost. Okay. Now the way you compute the cost is the cost of reaching the current node. Okay. From the root. Okay. Because you already traversed that, right? Up to that node in a tree. That is one cost. Plus, you are not done. Then you have to add the cost of reaching an answer node. And you're still going down from that node, right? Remember how we said B in or out, then from B you went to C in and out, and from C you went to D. So you're still traversing towards the solution. So the total cost is that GX and HX. Okay. So there's a puzzle here where we said that it's I think we all played this puzzle, right? Where what do you call that puzzle? I don't know in India. The numbers are out of alignment. You put them in order, and there's always one blank square. That's how you move the pieces, right? Then you bring them in order 1, 2, 3, 4, 5, 6, 7, 8. I used to solve that, but 16 number puzzle like that. Similarly, something similar to that. Okay. Now what this is showing is, hey, your initial state is you have 1, 2, 3, 5, 6, and 7, 8, 4. Okay. The trick is to come to that final state. I'm not showing final state which is solved, okay? I'm showing that final state, whatever it is. I want the numbers to be 1, 2, 3, 5, 8, 6, and 7, and 4. Okay? So how do you compare? And the cost function, I've given you the cost function here. Where we are saying, hey, GX is the number of moves so far. Remember, as you traverse the tree, that is the number of moves, right? GX. And then the HX is the number of misplaced tiles. Okay. And then we are saying that moving one tile in any direction, the cost is 1. Okay. Now, how many misplaced tiles are there visually looking at it? Can anyone tell me how many misplaced tiles are there? Misplaced means you compare the final state to the initial state, right? Are there any misplaced tiles? 1, 2, 3, 1, 2, 3, nothing. Okay, 3. How did you get them? What are the misplaced tiles? How did you get 3? So 6 is misplaced. Let's go row by row. 6 is misplaced. Right? What are the misplaced tiles? 6, 8, and 7, right? There you go. There you go. You got it. Perfect. Okay. So that is the cost function. Okay. Now what are we doing here? Now you're moving, right? You're building the tree. See that? So what did you do the tree here? You started off with 1, 2, 3, 5, 6, 7, 8, 4 like that. You can do different things, right? What are the combinations you can move? You moved 4 up. Okay, that is the leftmost branch. Okay, I think there was some mistake in the cost function, and if I vaguely remember. So why did I write the cost function of the left branch as 1 plus 4 equal to 5? Because you made one move. Okay, once you made one move, then you still have to count the number of misplaced tiles, right? So if I move 4 up, if I go back here, let me see. If I move 4 up there and 5, 6 are still there, okay? So imagine, let me do it here. So I moved 4 up here, right? Next to this one. Then how many misplaced tiles I would have? Because HX is the number of misplaced tiles. 4 would be misplaced tile, 6 would be misplaced tile, right? Misplaced tile. So there'll be 4 misplaced tiles. Okay, let me go back to this. Yeah. So if I move 4 up here, 1 is the movement, 1 move. That 1 comes from there. Plus, I have 4 misplaced tiles. That's how you get 5 here. Okay. If I do this one here, if you look at this second branch here, instead of moving 4, I've moved 6 here to the right. Okay. I want you to follow that carefully. Okay. I know the faculty member is nodding the head. He understood it for sure. Right. So along with me, I understood it too. Okay. So when you move 6 here, so you're keeping the final solution in place. I did not show what the final solution was. 6 is in the right place, right? If you go back here. Yeah, 6 came in the right place. Okay. And then you're left with only 2 misplaced tiles. 8 is misplaced, 7 is misplaced. Right? 8 has to go in the middle there and 7 has to go to the right. So that's why cost function here is 3. And so on. Okay. Now what are we doing here then? Right? Okay. So you're basically calculating the cost function. Then you want to take the least cost, right? Okay. You got it? Let me show. So when you're building the tree, there are the different combinations, right? What can you do? You can either move 4 there or 6 there, right? And you can move 3 there, right? You can move 3 down. When you do that, you get 5. Okay. Now, out of these 3, which branch you would follow to explore further? Obviously, the middle branch, right, where the cost function is equal to 3. Why would I want to take a higher cost path? I want to take a lower cost path. Correct? Faculty member, me Vanakala, our 2 girls are chatting away non-stop. You either want to have them to stop to the right, to your right. Yeah. And she's smiling now. You have a great smile, but you cannot distract people in the classroom. Okay? Not acceptable. Okay? I think we should give her a punishment, right? How many boys are there in the class? Approximately. Can you put it in the chat? Or how many girls? How many students are there in the class? She moved the video. In the class tarvata వాళ్ళందరికీ the girl should order them nice chai and biscuits, okay? That is a punishment for that girl. All of you guys go to the canteen. She's going to order tea for you and biscuits or an idli dosha, whatever you get. That's a very appropriate punishment for that girl, for disturbing us, for distracting me away from the flow of the lecture here. Okay, just changing the video to the boys doesn't help. I actually want to monitor that girl more to make sure she is not distracting anyone else. Okay. So you're still in the spotlight, okay? Remember, it's not just me who is watching you. It is all the other colleges, they are watching you too. Okay? Okay, so you want to follow the least cost here, right? But see how I'm building the tree, right? So that is the key thing. Now, visually I explained it. Now, how can we write an algorithm for it, right? Come here somewhere, okay? It's a huge algorithm, right? So obviously, if I say, I explain to you, go write the algorithm, it won't be easy, okay? You'll probably spend a month to try to figure that out. Very smart kids in a class, they'll figure it out in a day and then they do it, okay? So this is the algorithm now. Obviously, you want to trace it and then see that it works, okay? Now, so the key differentiation between backtracking and this one is what? One is backtracking is always depth first, whereas with branch and bound, we said it's breadth first. Breadth first is also nothing but the least cost approach. Okay, you're always taking the least cost approach. Okay, remember the keyword, because I know that in exams in JNTU, I mean, I heard a lot of horror stories as to how they are graded. I have my nephew, my cousin was stinging me, right? He is now in third year. Oh, you're in third year, right? Second semester, right? Oh, I think he is also in third year, second semester. Some exams happened in JNTU Hyderabad where he got 12 marks. A lot of students got 12 marks in some particular subject, they all failed. And they were asked to do a supplemental exam. Okay? But of course, it has since been corrected. They did re-evaluation and then he passed. That's a different story. So what I think would have happened was the instructor was probably seeing some kind of a keyword. So remember the keyword here, right? Breadth first, least cost. Okay? Execution time. Branch and bound takes less time. Why? Why does the branch and bound take less time over backtracking? If that is the question, what should be your answer? Your answer is because there's a bound. Bound means you are eliminating the non-promising branches of the tree. So you don't have to traverse the tree. That is the reason why branch and bound is more efficient than backtracking. Okay? Now space requirement. Okay? So space requirement obviously for branch and bound would be more because it's a little bit tough for you to understand that part because in backtracking you're building a tree, a system, building a stack. Okay, so as you're backtracking, you're building a stack, and then when you come out of that, when you backtrack, you're removing data from the stack and all that stuff. I don't know how to explain that beyond that. I'm sorry. Okay. More about operating systems and all that to understand that. Okay, so we'll move on from there. Okay? But in general, an educated layman's term, you should be able to say, hey, I'm taking the least cost approach. That's number one. It's breadth first. Number two, I'm also saving on execution time because I'm pruning the trees. I'm not traversing unpromising branches of the tree. By the way, I didn't keep track of the time. What is the time? 11:30. Okay, we still have time, right? 11:30. Are we done with the time? Are we? We still have time, right? Yeah, I think we have at least 1.5 hours. Okay. Okay. I have another puzzle here. Rat in a maze, right? How to get out of the maze, right? So some branch and bound algorithm example is there. I'll skip that for now. You can convince yourself as to how that works. Okay, but I do have the. Okay. Now there's another topic here called in branch and bound first in first out solutions. Let's look at what this is. Okay. First of all, what is branch and bound, right? We said we are finding optimal solution, okay, for optimization problems, okay? And then we are enumerating all the candidate solutions and discarding large subsets of fruitless candidates by using upper and lower estimated bounds, okay? We know that already, okay? So when you are doing that search tree, right? You're doing breadth first. When you say all the children of a node are generated before expanding any of the children, meaning that is breadth first, okay, as opposed to depth first. Now remember the code that I gave you. In the code, you had this concept of, okay, what is a live node? Live node is a node that has been generated, but whose children have not yet been generated. Now, E node is a node whose children are currently being explored, right? Remember, you build one level, go to the next level, and so on, okay? A dead node is a generated node that is not to be expanded, meaning you know that that is not a promising branch. You will no longer explore the territory, okay? That's what happened here, right? If you go back a few slides here, that's what we did here, right? We took only the middle branch, right? Because the other two branches are dead. There is no need to expand them in the least cost approach. Give me a second here. One second. My system froze. Give me a second. Okay, so here's an example. I'm pausing for a second. Give me a second, please. Sorry, that was a quick interruption. Okay, somebody put here. Yes. When did he put? Can you please explain again? I'm trying to explain through this illustration. You're talking about explaining the terms. I'm putting some. I don't know when you put that in the chat. If you're talking about this one, just type yes and I'll do that, okay? So let's look at this illustration here, right? So what are the live nodes when you're expanding things? Puzzle problem. Oh, I see, okay. You want me to come back to the puzzle problem. Wow, that was, okay. There's a request here to explain the puzzle problem, okay? So we'll start from here, okay? So here is the puzzle, right? On the left, we'll spend another 5 minutes on this. Somebody asked me to explain it again, okay? So 1, 2, 3, 5, 6, 7, 8, 4. Okay. We want to get to the picture on the right. 1, 2, 3, 5, 8, 6, and 7, 4 to the right. So far, so good. Okay. And then we have a cost associated. There are two costs associated, which we keep track of at every step of the way. One is the cost of how many moves we have made so far, the number of moves. Okay. And then after we move, how many misplaced tiles are still there? Because we still have to move them, right? If they are misplaced, that means I should move them, correct? So the total cost is the number of moves plus still the number of misplaced tiles. Okay. As somebody put it here, Sri Prakash put it, the answer 3, right? So the misplaced tiles to begin with are 3 here. Why? You're comparing it the initials to the final state, right? You want 1, 2, 3 initial state, they're like that. In the final state, 1, 2, 3 same. They are not misplaced. They are in the correct locations, correct? It's a table, right? Table is a cell, right? 1, 1, 1, 2, 1, 3, correct? First row, first column, first row, second column, first row, third column. So 1, 2, 3 are not misplaced. You have 5, 6 here, but you want 5, 8 in between. So 6 should be in row 2 and column 3 as per the final state, correct? But it is not. So 6 is misplaced. You agree? Okay. Now 8 should be in column in row 2, column 2, but it is not. So that is also misplaced. So that's 2. Okay. And then as Sri Prakash rightly put there, 7 is misplaced because 7 column 2. Okay. We get that. So, okay. So this is how it was, right? Initially, 1, 2, 3, 5, 6, 7, 8, 4. How do we arrive at that final state solution? What are the options that we have here? What are the options that I have? Somehow I have to move the tiles, right? What can I move to this empty tile here? The empty box. I can move 4, or I can move 3, or I can move 6. You agree? Correct? You get the table on the left. Moving 6, you get the table in the middle. Okay. And moving 3, you get the table on the right. Agree? Any questions on that? Who asked me to explain the puzzle problem? Sri Prakash, right? Yeah. So you're understanding it, correct? Okay. 1 second. Okay. Now, so you have these 3 branches. Now, when you have these 3 branches, at every step you calculate the cost function. Okay, that is C. What is the cost function? G of something plus H of something, right? One is move made. How many moves we made to move one tile? 1 move. That 1 is that. And the first digit there, 1, is related to the 1 move. How did you come up with the 4 on the left branch? That is how many misplaced tiles that you have compared to the final state. So the misplaced tiles they have compared to the final state in the leftmost picture is 4. Oh, what happened? Do you see my screen? Is the cost of move plus how many misplaced tiles. So you come up with the 3 branches because there are 3 possibilities. Now the next question for you is, which of these branches you should continue to explore further, right? The goal is to always have the least cost solution, right? So if you look at the least cost solution here, the middle branch where the cost function is 3 is what is more promising. Okay. Now you come to this one, you expand. When I say what next, then you're expanding 1, 2, 3, 5, 6, 7, 8, 4 in this way with the middle tile empty. Okay. See, now you have 1, 2, 3, 5, 6, 7, 8, 4. Okay. Now, what are the things that you can do in this tile here now? What can you put back there? You can put 8 there, correct? You can put 8 there. That is one branch. Okay. You can put 5 there in that empty thing. That is the second branch. And then you can put 2 there. That is the other branch. Correct? Now, what is the cost? When you see cost on the left side, it's 2 plus 1. What is 2? 2 is the number of moves that you made so far. That is 2. Okay? Because in the first one, you did 1 move already. Now you did second move. And the cost, now how many misplaced tiles are there in this? Correct? In the case of middle branch, you have 2 plus 3. There are 3 misplaced tiles. And in the third branch here to the right, you have 3 misplaced tiles. That's 5. So what is the lowest cost? On the left side. Okay. Now what do you do on the left side once you have that? There are 2 paths. Correct? You can either move 4 to the branch here or move 7 to the empty slot. Okay. Which of them has the lowest cost? The one on the right. Correct? Now, is the one on the right the solution that you are looking for? If you compare 1, 2, 3, 5, 8, 6, if you go back to the first slide here, that's exactly what you wanted. Did we reach the final state? We did. So you stop. Got it? Okay, questions? Very interesting problems, huh? That's why I love data structures. It's like a never-ending, what I call it as excitement to solve these things, right? So I gave another example of rat in the maze. Students can convince yourself outside of the class. And then you have branch and bound FIFO solution, okay? So to understand that one, right, before I did that, I just introduced some terminology here. What do we mean by a live node? What is E node, right? So when we say live node is a node that is generated but whose children have not yet been generated, right? E node is the node that is under consideration, right? So in the case of picture here, 1, 2, 3, 4, and 5 are live nodes. Why? Because no children for them have been generated yet. Okay. And then you have the second middle figure there. When you see there, okay, you are exploring from the left 2, 3, 4, 5, 5, 4, right? The way, depending on the tree that is built, you are building it from breadth first, going from the left. So since you're considering the E nodes or active nodes in the order that they were built in the tree, that's why it's called FIFO, first in, first out. Whereas in the rightmost figure, you see that when you build a tree 1, 2, 3, 4, 5, 4 and 5 nodes were built the last. 5 was built the last. So then you explore 5 first. Okay? That's why you say 6 and 7. Explore means you're building the tree, subtree. After you do 5, then you do 4. Okay? Remember, it's breadth first. So you build the branch and then you move to the left in the last and first out. But in our case, we want to explore first in, first out. Okay? So when you do breadth first search, basically you're doing a FIFO search in terms of live nodes. Okay? Now when you have live nodes, you have to maintain a queue. If you look at the algorithm, that's what it did here, right? I said you people have to convince yourself of the algorithm, right? Where Where did I put the algorithm here? Before that in the maze. See this one? The algorithm talks about a live node set. Okay. So a set is nothing but a queue, right? Okay. And we have seen how to write a queue, right? In the beginning of the class. Actually, we learn about that in the second year, second semester course too. Okay. So it's a FIFO search in terms of the live nodes. Okay, and whereas depth first search is a live first search in terms of the live nodes. Okay, there's some theory there. Okay, so we are revisiting the example of the tiles here, how we did that one, just to show you how this has been done, right? What was the first branch? We are talking about taking the one where that's on the left side. So then I give an exercise. Again, we don't have time to do it here. You have to do it outside the class, right? So you want the bullet points, right? There's only one live node. Why? Because nothing has been put on the board. It's an empty board, okay? Now, once you place the first queen, okay, that live node status would change to E node. E node means the one that you're going to be exploring. See, the definition is given there. E node is a live node whose children are currently being explored. Okay? So you're expanding that. Okay? Now, when you're expanding an E node, you want to generate all of its children. Okay? The children of that first queen, wherever you put. Where do you put the first queen? Based on our algorithm, we put it in A11, right? The first row, first column. Okay? Then it's a 4x4 board. So where do you put the children? You can put the children in the first column, second column, third column, fourth column. Okay? Then you go to the E node. Then you take the one in the first column. Then you expand that node. Okay? So that is how the algorithm proceeds. I kind of show the encoding of that algorithm. Again, I'm not going through all the details here. You have to slowly convince yourself by reviewing these slides here and coming back to me with questions in the next class, right? So these are the live nodes, row 1, 1, 1, 2, 1, 3. Okay, and so on. Okay, and the same example I show how we do the backtracking. We did that example already. So it shows you the same thing again repeated here. We did that in the last class, right? Or the last but one class. Okay. Algorithms, backtracking versus the branch and bound. Which of those things would give you a better solution is what we have to figure it out. Okay. So I give the solutions there. You did this picture here already. What is the time? Is it already time? Yeah, we only have about 7 minutes. Okay, got it. Okay, that is the essence of the branch and bound, right? So when you do the breadth first search, it basically is nothing but a breadth first search or a FIFO algorithm. It turns out it will come into a FIFO algorithm. Okay. So that's pretty much it with respect to this chapter, but I'll wrap up some loose ends in the next class. I know a lot of you went to Holi and some of you are ready to go to Holi, I don't know. Let me know if you have any questions. Maybe, I don't know. I think I posted this here. So what I want students to do is review these slides because all the notes are given there. I explained to you at a high level how this branch and bound works. You just have to trace, as we always do, the algorithm. I gave you the board there, for example, for the 4 queens. Do it with backtracking, do it with branch and bound based on the code that I gave.